Rahim. Assalamu alaikum dear students. I am Arif and I welcome you all in today's session. To access the notebook for today's session, you can access my course page on my personal website arifpart.me. The other way is to download all the notebook files from course GitHub account arifpucit, and all the notebooks for this course are housed in this public data science repository. Well, this is the Jupyter Notebook dashboard running locally on my machine at port 8888, and here is the notebook for lecture number 6.26 of the 6th module machine learning for the course titled Tools and Techniques for Data Science. Well, this session is a continuation of previous session where we covered all the basic probability concepts including joint, marginal and conditional probability, using quite a lot of examples, using paper pencil as well as using Python code. Well, if you want to revise those concepts, please watch that lecture which covers all the related concepts required to understand Bayes theorem and naive Bayes classifier, which is actually the title of today's session. And here is the learning agenda of today's session. We will start with the Bayes theorem, its proof and examples for a crystal clear understanding. Then I will give you an overview of naive Bayes classifier, and we'll do 4 examples that will cover datasets having discrete input features. And of course 2 datasets having continuous input feature that will use Gaussian naive Bayes for classification. At the end of the session, I will give you some tasks for you to do at your own. My dear students, rest assured that after watching this entire video, there will not be an iota of ambiguity as far as applying naive Bayes classifier on different types of data sets. I think enough of motivation. Get your oxygen tanks ready and let's do a scuba dive. Okay, we all know that conditional probability is the probability of an event A occurring given that another event B has already occurred. In the previous session, we have seen that the formula to calculate the conditional probability of A given B is equal to the joint probability of the 2 events divided by the marginal probability of the event that has already occurred. And this Bayes theorem is actually a way of calculating this conditional probability without the joint probability. And this theorem was introduced by Thomas Bayes and was first published in 1763, quite a time ago. Well, this theorem is the cornerstone of Bayesian learning methods. That is a paradigm for constructing statistical models based on Bayes theorem, and the formula for Bayes theorem is shown in magenta color over here. And before I describe it, let me give you a walkthrough as to how we can derive this formula shown in magenta color from the formula of conditional probability shown in equation 1, that is probability of A given B is equal to the joint probability of event A and B divided by the probability of B. Well, this equation 2 shows the probability of event B given that event A has already occurred, and if we multiply both sides of this equation 1 and this equation 2 by probability of A, we get these 2 equations 3 and 4 respectively. And since probability of A intersection B and probability of B intersection A are same, so we can equate these 2 equations, this equation 3 and this equation 4. If we equate them, my dear students, we get this probability of A given B times probability of B equals probability of B given A times probability of A. And from this you can easily see that probability of A given B will be equal to probability of B given A times probability of A divided by probability of B, and this is what the formula of Bayes theorem is. That is shown in magenta color over here as well and over here as well. My dear students, in literature you will come across these three versions of the formula, and the first one is mostly used by statisticians where A and B are two events. This middle one shown in blue color is used by data scientists and machine learning engineers, where this lowercase h is the hypothesis whose probability is to be computed given the observed data represented with this uppercase D. My dear students, in our video, since we are using capital X to represent the input features and lowercase y to represent the output label, which we want to predict actually, therefore I will use this third formula shown in green color over here in this video, and this probability of y equals k given x is called the posterior probability. That is, we want to calculate the probability that output label y has a value of k given the input features x. And this probability of x given y equals k is the reverse of posterior probability called the likelihood. And probability of y equals k is the prior probability, and this probability of x in the denominator is known as the evidence or normalization constant, and it must be non-zero. I hope this formula is clear. Let's do a few examples for a better understanding. These two examples are very basic. Let me describe this first one, which says what is the probability, rather the conditional probability that a card drawn from a deck of playing cards is queen given that it is a card of spades. So using this green formula of Bayes theorem, we can calculate this. Well, the probability of randomly selected card being queen is 4 over 52, as there are 4 queens in a deck of playing cards. Similarly, the probability of a randomly selected card being a card of spades is 13 over 52, as there are 13 spades card in a deck of playing cards. And finally, the probability of x given the card is queen, that is the probability of the card being spades given that it is a queen, is 1 over 4, as there are a total of 4 queens and only one out of them can be a queen of spades. Now we substitute these 3 probabilities in this green formula, and we get 1 over 13, which is the probability of a card being queen given that it is a card of spades. I hope this is making sense, especially if you have gone through with our previous video. Please do go through with this example at your own time, and let me move on to this example 3. Suppose there is a factory having 3 machines, say M1, M2 and M3, which produce 20, 30 and 50 items respectively every day. That is, a total of 100 items are manufactured daily in that factory. Moreover, the machines M1, M2 and M3, they produce 5, 3 and 1% defective items respectively out of the total items they produce. Now suppose an item is selected at random. The question is, what is the probability that it is manufactured by machine M3 given that it is defective? Once again, we need to actually calculate this. Probability of y is equal to M3 given x. We can use this Bayes theorem to calculate this probability, and we can read it as probability of y equals M3 given that the item is defective. So probability of y equals M3 is the prior probability. That is, the item is manufactured by machine M3, and that is 0.5 over here. Fine. And the probability of x given y equals M3 is the likelihood, that is, the item is defective given that it is produced by M3, and which is 1 over 100, that is 0.05, calculated over here. And finally, in the denominator, this probability of x is the probability of defective item that can be produced by either machine M1, M2 or M3. Therefore, the overall probability of an item to be defective is equal to the sum of the probabilities of a defective item being produced by either M1 or M2 or M3, which is shown over here. So in the denominator, you can see the sum of the three probabilities. Probability of defective item produced by M1 plus probability of defective item produced by M2 plus probability of defective item produced by M3. And of course, we can calculate these three joint probabilities. For example, this probability of x intersection M1, this will be equal to the probability of x given y equals M1 times the probability of y equals M1. And similarly, you can use the same conditional probability formula for the rest of these two probabilities in the denominator, and they will be expanded like this. And finally, substituting the values of all these probabilities, we get our answer, that is 0.2083, which is actually the probability of an item produced by M3 given that it is defective. My dear students, I hope this is clear. If not, please go through the conditional probability portion of my previous video. Okay, I think now it is time to talk about the main agenda of today's session, that is naive-Bayes classifier, which is actually a probabilistic machine learning algorithm that uses Bayes' theorem for supervised machine learning classification. And remember, unlike deterministic classifiers like k-nearest neighbors, support vector machines and decision trees, which just output a hard label for each sample without providing probability estimates for the classes, this probabilistic classifier, like logistic regression, naive-Bayes and neural network, they output probability estimate for k classes and then assign the label to the sample based on these probabilities. Moreover, my dear students, this naive-Bayes classifier is called naive because it assumes that input features are independent of each other, which is rarely, of course, the case and is almost never true. And even then, it performs really well in applications where the features are not independent of each other. Moreover, in comparison to other machine learning algorithms, this naive-Bayes classifier is quite fast and therefore can be used for making predictions in real time. Okay, please go through with this textual information. And instead of discussing all the theoretical aspects of naive-Bayes classifier in the very beginning, I am taking a different approach. We will actually go through with different examples having increasing complexity, and I will keep explaining the related concepts as the need arise. So let us start with a very basic example of a dataset having a single input feature with categorical values and an output label. The snapshot of the training dataset is shown over here in this table, having 100 observations with one input feature, that is color of a fruit, having three possible values, red, green and orange. The output label has two possible values or classes, apple and orange. Well, this input feature color is denoted by uppercase X and the output label is denoted by a lowercase y. The objective is to predict the fruit given its color. For example, Given this data set, you need to build a naive Bayes classifier so that when a new instance of a fruit is given, say of green color, you need to predict what fruit it is. So the Bayes theorem comes for our rescue. We actually compute two probabilities, that is probability of y equals apple given its color is green, and probability of y equals orange given its color is green. And later we compare the two probabilities. Whatever probability is larger is the predicted output label. I hope this makes sense. Okay. Well, the first step is to create a contingency or frequency table from the training data set. In the previous lecture, we have done this using Panda's cross-tab method. I have already created the contingency table as shown, and that has been generated from this table. I hope this is making sense. For the single input feature X, we have three categorical values, red, green and orange. For the output label Y, we have two classes, apple and orange, along the columns. So this first column tells us that there are 33 red apples, 20 green apples and 1 orange apple. That is a total of 54 apples in the data set. Similarly, this second column tells us that there are 0 red oranges, 7 green oranges and 39 orange color oranges. That is a total of 46 oranges are there in the data set. Well, this total column in blue color tells us that there are 33 red, 27 green and 40 orange fruits in the data set. A total of 100 fruits. So given this contingency table, we can easily calculate the marginal probabilities as well as the joint probabilities by dividing all these values by the total number of fruits, that is 100. Okay. Well, in step 2, I have calculated the marginal probabilities, that is probabilities for y equals apple and y equals orange. In step 3, I have calculated the marginal probabilities for the single input feature, that is color. So the probability of x equals red is 33 over 100. Probability of x is equal to green is 27 over 100, and the probability of x is equal to orange is 40 over 100. And in step 4, I have calculated just the two conditional or joint probabilities, that is the probability of y equals green given x is equal to green given y equals apple, which comes out to be this 20 over 54. And the next probability is the probability of x equals green given y is equal to orange. X is equal to green given y is equal to orange, and that comes out to be 7 over 46. 7 over 46. Great. And finally, my dear students, we just need to substitute or plug in all these probability values into the naive Bayes formula that we have discussed above. And the probability of y equals apple given x equals green, this comes out to be 20 over 27, while the probability of y equals orange given x equals green comes out to be 7 over 27. And since this probability of y equals apple given x is equal to green, that is 20 over 27, is greater than the probability of y is equal to orange given x is equal to green, that is 7 over 27. Therefore, we classify the fruit given that its color is green as an apple. My dear students, do note that in this example from this contingency table, you can see that the output label y has only two outcomes, that is apple or orange. Therefore, we have computed two probabilities, In case of more than two classes, we will compute probabilities of belonging to each class, and whichever probability is larger, that will be our output label. Also note that in step 5, the value of this denominator for calculating both the probabilities is same. That is, probability of x is equal to green, that is 27 over 100. And since we are just comparing these two probabilities, therefore we can ignore the term in the denominator. And the simplified formula for naive Bayes is shown in green over here, where I have just injected the proportionality instead of the equality. So we have just removed the probability value in the denominator. Well, my dear students, before moving on to the next example, having multiple input features, let me describe the zero frequency problem that you may come across, and its a solution as well, called Laplace smoothing. Suppose we are given a new instance of fruit having red color. Previously we have predicted a fruit having green color, and this time we want to predict a fruit having red color. In the contingency table over here, you can observe that we have 33 red apples and 0 red oranges. If we compute the two probabilities, that is probability of y equals apple given x is equal to red, and probability of y equals orange given x equals red, the two probabilities comes out to be 33 over 100 and 0. And we can easily classify the fruit as an apple, because the probability of being an apple is greater than the probability of being an orange. This seems to be working fine, but my dear students, if we have more than one input feature, the entire probability will become 0, because one of the frequency of a feature is 0, and this is what is called zero frequency problem. And we can solve this problem using a technique called Laplace smoothing. Excuse me, which is applied by just adding a 1 count to the numerator and adding the possible values of the feature to the denominator. Here, since we have 3 values of the feature color, that is red, green and orange, so we have added 3 in the denominator and 1 in the numerator, and this is shown over here. So even after applying Laplace smoothing, we still classify the fruit having red color being apple. And note that we don't have a zero frequency over here, zero probability over here. And I hope this zero frequency problem and Laplace smoothing is clear to you all. We will of course keep applying this Laplace smoothing in the rest of the data sets as well for better understanding. Let's move ahead. And now consider this hypothetical training data set that describes weather conditions as shown in this table. And this time there are 3 input features and 1 output label, and a total of 15 observations. Excuse me. This input feature outlook, or lowercase x1, can have 2 possible values, cloudy and sunny. The input feature temperature, or x2, can have 3 possible values, cool, mild or hot. The third input feature, humidity, or lowercase x3, can have 3 possible values, low, normal or high. And based on these 3 input features, the output label rain can have 2 possible values, yes or no. Well, we have discussed as to how we can apply naive-based classifier on a dataset having single input feature. Now we need to extend the formula of naive-based classifier for multiple features. And once again, the word naive. The word naive means that the algorithm assumes that input features are independent of each other. And in this dataset, this means that changing the value of temperature does not directly change the value of humidity. However, in reality, we know that the temperature and humidity are very much related to each other. Anyways, this first line in green color shows the naive-based formula for multiple input features. As you can see, instead of just x, we have x sub I over here, where I can range from 1 to m, where m is the number of input features, and for this example m equals to 3. In the second equation, you can see I have expanded the probability of x sub I y equals k to probability of x1 given y equals k times probability of x2 given y equals k times, and so on to probability of xm given y equals k. To be more mathematically precise, we can write the naive base formula as this y hat, which is equal to the argmax of y, probability of y equals k times the product of conditional probabilities of x sub I given y equals k. I hope this is making sense to you all. This argmax of a function is the value of the output at the maximum, and for this data set k can be yes or no. So argmax will return the value of the output label y that has the maximum probability, which will be assigned to this y hat. And my dear students, this is mathematically called the maximum a posteriori or map. This map, maximum a posteriori decision rule, since it chooses the hypothesis that maximizes the posterior probability. Okay, now let's assume, let's do this example and assume that on a particular day the outlook is cloudy, cool, temperature is cool and humidity is normal. So this is a new input vector, and based on this input vector we need to classify whether the output label will be a yes or a no. Well, to use naive Bayes classifier for this, we need to compute these two conditional probabilities, and whichever probability will be greater we will predict accordingly. That is, probability of y equals x given x1 equals cloudy, x2 equals cool and x3 is equal to normal, and probability of y equals no given the same input vector. So first we need to create the contingency table, and since we have three features, outlook, temperature and humidity, therefore we need to construct three contingency tables as shown over here. So please do map this table, how we can construct three contingency table, one for outlook, one for temperature and one for humidity. I hope this is very simple. You can in Python you can easily use the cross tab method. We have done these many a times in our previous session. Okay, in step 2 I have calculated the marginal probabilities for each output label, that is probability of y equals yes and probability of y equals no, and that comes out to be 6 over 15 and 9 over 15. 6 and 9. In step 3 I have calculated all the conditional probabilities for the three input features given y equals yes as well as for y equals no. I hope this is making sense. You can easily calculate these probabilities from these tables. And finally we just plug in all these probability values into the naive Bayes formula, and since the probability of y equals yes given the weather conditions are cloudy, cool and normal is greater than the probability of y equals no given the same conditions, that is 0.074 is greater than 0.009, therefore we can easily predict that it will rain. My dear students, I hope the calculations are clear. If they are not, please take up a paper pencil, do all this math yourself, and then it will be crystal clear to you all. Okay, so let me do one more example using the Titanic data set that we have discussed in the previous session in length. So to keep things simple, let me just take the two columns, the passenger class and sex, and the output label survived. So this is our toy data set. We need to use knife bias classifier so that you give me the P class and sex of a passenger, and I will predict that the specific passenger will survive or not. Okay. So these two cells are using Panda's cross tab method to construct the two contingency tables for the sex column and the P class column. Well, I have also shown a bigger picture of these two tables for better understanding. So these are the two contingency tables. This is for the sex column and this is for the P class column. And from both these tables, my dear students, you can see that the probability of y is equal to survived is equal to 342 over 891, while the probability of y equals dead is 549 over 891. And similarly, the probability of x1 equals female given y is equal to survived, x1 is equal to female given y is equal to survived, is 233 over 342, and the probability of x2 is equal to P class 1 and y is equal to survive, so x2 is equal to P class 1 and y is equal to survived, is 136 over 342. In the same fashion, you can calculate the rest of the probabilities as well, and after plugging in the probabilities into the naive Bayes formula, you can see that the probability of survival given x1 equals female and x2 is equal to P class 1 is greater than the probability of y equals dead given x1 is equal to female and x2 is equal to P class 1, and therefore we can easily predict that the passenger will survive. Great job done. Okay. Well, my dear students, a naive Bayes classifier is mostly used in natural language processing domain. So let me give you a very basic example of applying naive Bayes classifier on textual data as well. Well, consider this labeled toy dataset having just 4 sentences or 4 single line documents. Each is labeled as either positive or a negative sentence. Given a new sentence, and that is I am playing cricket and happy, we need to classify it as positive or negative using naive Bayes classifier. Well, as usual in the first step, we need to construct the contingency table or the frequency count of all the words in both the positive and the negative class. Well, I have not done any of the text pre-processing to keep things simple. I hope you can construct this table over here using this above toy dataset by hand. And now to classify this sentence, that is I am playing cricket and happy, we need to compute these two probabilities shown in green color, and whichever will have the higher probability will win. Okay. As usual in step 2, we compute the probabilities of each of the output label and the probabilities of both positive and negative class outcomes. And there are probability of y equals positive is 1 over 2, y is equal to negative is 1 over 2. Fine. And in step 3, we calculate the conditional probabilities of the words I am playing cricket and happy for both the positive class as well as the negative class. And for example, the probability of the word happy, given that it belongs to positive class, is 2 over 13. If you see this table, happy is over here, positive class 2 over 13. And similarly, the probability of this word happy, given that it belongs to negative class, that is y is equal to negative, if you come up over here in the table again, happy, negative column, this value 1 over 13. So this is 1 over 13. And similarly, you can map all these probabilities from these table. Okay. So in step 4, we just substitute all these probabilities into the naive Bayes formula. And since the probability of y is equal to positive, given this sentence, is greater than the probability of y equals negative, given this sentence, we can easily classify that the given sentence belongs to a positive class. You see this value 0.000024 and this value 0.0000121. So this value is a bigger value, therefore we assign a positive class to this sentence. Great job done. My dear students, this example is just an abstract level overview of using naive Bayes classifier for text classification. Interested students can watch my separate playlist on natural language processing for details. Okay. I think enough of examples of naive Bayes classifier for datasets having discrete input features. Let us now do 1 or 2 examples of continuous input features. So far we have seen that the axes or the input columns of our dataset are categorical variables. But what if they are continuous variables? For example, if you consider this hypothetical data set showing the measures of the prostate specific antigen, that is PSA concentration from blood samples of let's say 14 persons, and out of these 7 are actually patients of cancer while 7 are healthy. We have just one input feature, that is PSA level, which is a continuous variable, and the output label has 2 possible values, that is cancer and healthy. And now our $100 question is how to compute the probabilities when X is a continuous variable. Well, the answer is Gaussian naive Bayes model, which assumes that the input features follow Gaussian distribution. That is, this PSA, this column follows a Gaussian distribution. So other than assuming that the feature variables are independent to each other, this model also assumes that the input feature variable follow a Gaussian distribution. And remember, Gaussian naive Bayes model can still be used even if the data is not normally distributed or even if the feature variables are not independent. However, if these 2 assumptions are not met, the model may not give you that much good results. Anyways, I hope the dataset is clear to you all, and for a better understanding, I have given the visual representation of the data as well, which is taken from tilestats.com. The only input feature is the PSA level shown along the horizontal axis. These green circles represent the healthy persons, while the orange circles represent the cancer patients. Now suppose that we want to predict if a person of PSA level 2.6 microgram per liter has a prostate cancer or not. So this is what we need to do. Well, this can be done using Gaussian naive Bayes model, whose probability density function is shown in magenta color over here. This complex function is the Gaussian function. We just need to calculate this mean and this variance of this PSA column over here for the cancer patient and healthy persons separately. And then we need to just plug in those values in this formula with x is equal to 2.6, because this is what we want to predict. And we get the value of this function for both the cancer patients and healthy persons. And whichever value will be greater, we will predict accordingly. So let's do this practically for a better understanding. So if we compute the mean and standard deviation of the healthy group, it comes out to be 1.5 and 0.61 respectively. Now if we plug in these two values along with different values of x or PSA in this probability density function, we will get this curve, this bell-shaped curve, showing the Gaussian or normal distribution of a healthy person, shown in green color over here. I hope this is making sense. You can always do this practically using the Python code. And my dear students, in the similar fashion, we can always calculate the mean and standard deviation of the cancer group as well, which comes out to be 2.8 and 0.82 respectively. And by substituting these two values along with different values of x or PSA in the PDF of Gaussian distribution, we get different values which, if plotted, will give this bell-shaped curve shown in orange color over here for the cancer patients. Do note that since the PSA values in the cancer group has larger spread, therefore the Gaussian curve is wider and has a lower peak as compared to the healthy curve. I hope the bell-shaped curves for both healthy person and cancer patients are clear to you all. And my dear students, now in order to predict whether a person with PSA level of 2.6 is healthy or cancerous, we just need to plug in x is equal to 2.6 in this formula along with the mean of 1.5 and variance or standard deviation of 0.61, we get 0.13. And if we plug in the values for the cancer group, that is 2.8 and 0.82 in this formula, we will get 0.47. And this is graphically represented in these two graphs for better understanding. Excuse me. My dear students, remember these two values, that is this 0.13 and 0.47, they are not the probabilities, rather are the values of a probability density function or the height of these curves when the PSA value is equal to 2.6. So this is 0.13 for the healthy person, and this is 0.47, this is the height. And you all know that the probability in case of continuous distribution is the area under the curve. So the last step is to substitute these values in the naive Bayes formula over here to calculate the probability of y equals healthy given PSA equals 2.6 and probability of y equals cancer given PSA equals 2.6, and we get these two values. And since this 0.235 is greater than 0.065, therefore we classify that the person has cancer. Great job done. Okay. Well, my dear students, let me extend the same example by adding one more input feature to the same data set. and that input feature is the age column as shown in this table. And suppose we want to predict if a person with PSA level of 2.6 and an age of 70 years has prostate cancer or not. Great. As done in the previous example, first we will calculate the mean and standard deviation for both the input features and for both the groups separately. And the final values are shown over here. Please do the calculation at your own time. And now we calculate the conditional probabilities for both the groups. And first I have calculated the value of probability density function for PSA equals 2.6 given cancer, which comes out to be 0.47. Then I have calculated the value of probability density function for age equals 70 given cancer, which comes out to be 0.055. And similarly you can calculate for the healthy group as well. Please spend some time to do these calculations yourself. And now in the last step, we just need to substitute these values in the Naive-Bayes formula to calculate the probability of y equals cancer given PSA equals 2.6 and age is equal to 70, and the probability of y equals healthy given PSA equals 2.6 and age is equal to 70. And since the posterior probability of cancer is greater than the posterior probability of healthy, therefore we classify that the person has cancer. Great. Okay, my dear students, now here are the tasks for you to do for a very crystal clear understanding. After you will do all these 2-3 tasks, you will have no doubt about the application of Naive-Bayes classifier. Consider this toy data set having 10 instances or observations, each having 3 attributes A, B and C. The output label class has 2 values, positive and negative, and given this data set you need to use the Naive-Bayes classifier and predict if the new instance having A equals 0, B equals 1 and C equals 0 belong to positive or negative class. I hope this will be a piece of cake. And this is task 2, where the dataset has the 3 input features, height, weight and foot size, and the output label is gender of the person, being male or female. Once again you need to use the Gaussian Naive-Bayes classifier and predict the gender of a person who is having a height of 6 feet and weight of 130 pounds and foot size is 8. I hope you will be able to do this after going through the examples that I have done in today's session. And finally, this data set, this is the third task. This has actually 4 attributes or input features: outlook, temperature, humidity and wind. And the output label is play tennis, having 2 values, yes or no. Out of these 4 attributes, this outlook and wind, these 2 are discrete value attributes, while this temperature and humidity, they are continuous value attributes. Well, given this data set, you need to once again use the Naive-Bayes classifier and predict the new instance. Outlook equals overcast, temperature equals 60, humidity equals 62 and windy equals false into either one of the classes, that is yes or no. And do not forget to use the Laplace smoothing for this task. Okay, my dear students, I'm sure after going through all these examples discussed in today's session, you must have now a very clear understanding of Naive-Bayes classifier and how to apply it on different types of dataset. Well, if you have liked today's session of mine, please do subscribe my YouTube channel and share it with your friends. I wish you all the best, happy learning and Allah Hafiz.